Hello everyone, Mr. Cron here. In this video, I'm going to be deriving the 5 kinematic equations. Now, the reason that we have 5 kinematic equations is because each one doesn't contain one of the 5 variables. So we have distance, acceleration, final velocity, initial velocity, and time, and every equation contains 4 of the variables with one being left out. So we'll know we'll have all 5 when we have an equation for each one of these boxes. So let's start this off. To start, you need to draw a general velocity time graph. So this is going to be time and velocity. And I'm going to start at an initial velocity and accelerate to a final velocity. So this will be my initial velocity, and this will be my final velocity. Now, the amount of time that takes is my change in time. So from this time to this time is my change in time. And you'll also notice here, this height on the velocity to this height is going to be my change in velocity. How much does my velocity change? And my change in velocity can be found by taking my final velocity minus my initial. So the first thing I'm going to notice here is that my slope of any graph is equal to my rise divided by my run. And in this case, the rise is my change in velocity and the run is my change in time. And I'm going to define how much my velocity changes divided by my time as acceleration. So my acceleration is change in velocity divided by change in time. And now I'm going to do some algebra, and I'll multiply both sides here by change in time. So this will cancel with that, and my change in time will come over to this side. Once I've done that, I'll rewrite this up here. So I've moved that around. I'm also going to switch change in velocity and a delta t to the opposite side. So I'll have change in velocity is equal to acceleration times time. And change in velocity, I said here, is Vf minus Vi, so I'll expand that. Vf minus Vi is equal to acceleration times time. I will add Vi to both sides. That will cancel with that. And once I've done that, I now have my first kinematic equation. Final velocity is equal to initial velocity plus acceleration times time. So I'm going to put that in here. You'll notice it has all 5 of the things except no distance. So I'll put it in this first one. Final velocity is equal to initial velocity plus acceleration times time. Okay, now for the next part. I also know that my change in distance is equal to the area under a velocity time curve. So the area under this line is going to be equal to my change in distance. Now I can find that. I know the area of a rectangle is always going to be my base times my height. So my base here is delta t, and my height, this isn't a rectangle, but if I take the average of my 2 velocities, so here if I add up Vi and Vf and divide by 2, I'll get some average velocity. So rather than having a triangle on top of a rectangle, I'll just turn it into a big rectangle, like so. And that is exactly how I get my second equation. I take my average of my velocities and I multiply it by my time. And I also know here that average velocity is my initial plus my final divided by 2 times my time. This is another kinematic equation. It's got all of the items except acceleration. So I'll put this one in over here. Change in distance is equal to Vi plus Vf divided by 2 times my change in time. Now I could have 1/2 out front and then Vi plus Vf, or this style. Either way, those are the same, so I'll just leave it like this. Okay, the next one. I'm going to figure out my change in distance by calculating the area under this curve in a different way. I'm going to calculate the area of the bottom rectangle, and I'm going to add in the area of the triangle on top, like so. I'll add in here that the area of any triangle is equal to the base times the height divided by 2. Because here, if I'm trying to find this entire rectangle, that would just be base times height, but I'm dividing it in half. So that's where the divide by 2 comes. Okay, so the area of this large, or the bottom rectangle here, is going to be my base times my height. Well, that's my time times, it goes up to VI. So I'm going to go VI times time plus the area of my triangle is going to be my base times my height divided by 2. So I'm going to put 1/2 out front instead of the divide by 2. My height of this little triangle, I apologize for the squiggles, that's just from using my mimeopad here, but this is delta V, and the base is time. So that's going to be delta V and time. Now, I'm going to replace delta V here with acceleration times time, because here I defined change in velocity is acceleration times time. So I'm going to take this and stick it in right here and then simplify. So change in distance is VI delta T plus 1/2. And I'm going to have A delta T delta T. I'm just going to go straight ahead and write that A delta T squared, because the delta T times delta T is delta T squared. And again, this one has no VF, so I'm going to put that in for my third one. Change in distance is initial velocity times time. Let me erase that. Initial velocity times time plus 1/2 A delta T squared. All right. Now, another way to solve that same kind of question is to find the distance as the area of the entire rectangle, and then I'll subtract out that top triangle. So here, if I found the area of the whole thing like this, and then subtract out this triangle, I would also find the same distance. So here, I'm going to find my change in distance. The area of the large rectangle, well, it's VF times time, because that's how tall it is. And then subtract 1/2, my base is time again, and my height is also change in velocity, same as before. Change in velocity times change in time. This is a very similar derivation to the last one. So same thing here. My change in velocity, I already know, is A delta T. So I'm going to leave that here. I'm going to put A delta T in, and I'll get change in distance is final velocity times time minus 1/2, and then acceleration delta T squared. This is my fourth kinematic equation. It has everything, but it has no VI. I'll put that one here. VF delta T minus 1/2 A delta T squared. Okay, on to the last one. For the last one, I need no time, right? I have all the other ones, I have no time. So what I'm going to do is I'm going to use equation 1 and equation 2 to solve for time both, and then make those two things equivalent to each other. So here, let me show you what I mean. Here I have velocity equals A delta T. So if I change that around, if I divide both sides by acceleration, I'll get change in time is equal to change in velocity divided by acceleration. That's from equation 1. Now, from equation 2, if I divide both sides by average velocity, I will get change in time is equal to my distance divided by my average velocity. Okay, so I got two things equal to time. So I'm going to make those, like this term and this term, equal to each other and solve. So let me find a different color. I'll use gray for this. So I'll do that over here. So I have change in velocity divided by acceleration is equal to change in distance divided by my average velocity. Now I'm going to cross multiply here, so my acceleration will come up there, my average velocity will come up there, and I will get average velocity times change in velocity is equal to acceleration times change in distance. Okay, now I'm going to expand this out. I know average velocity is I add them together and divide by 2. I know change in velocity is VF minus VI. So let me do that. So VF plus VI all divided by 2. And then change in velocity is VF minus VI. That is all equal to acceleration times change in distance. Now I'm going to multiply both sides by 2, and the 2 will come over to this side. I'm running out of space here, so let me just do that quick. Multiply by 2, that cancels. Multiply this by 2. And I'm going to have to use FOIL. So use FOIL. Remember, first, outside, inside, last to multiply a binomial by a binomial. So VF times VF is going to give me VF squared. VF times negative VI is going to give me minus VF VI. And then my inside, VI times VF, is going to give me a positive VF VI. And VI times negative VI is going to give me minus VI squared. And that's all going to equal 2A delta D. Now you'll notice here I have a positive VF VI term and a negative VF VI term. So those are going to cancel each other out. And let me just finish this one up here. I have VF squared minus VI squared is equal to 2A delta D. And lastly, I just have to add the VI squared to both sides. VI squared, that will cancel. And I'll have final velocity squared is equal to initial velocity squared plus 2A delta D. And this equation has no time, so those are my 5 VF squared. Those are my 5 kinematic equations. VI squared plus 2A delta D. And we drove those all from just a straight up velocity time graph where I start at an initial speed and at a final one. All right, that's it. Look at this, watch this as many times as needed so that you understand it, and good luck.